In this video, we're going to talk about the center of mass, moment of inertia, and we'll go over what an extended system is all about. And we'll apply this to two different problems, one of which is basically a yo-yo unraveling, and another one is a mass which is dropped from a certain height and it compresses once it collides with the tabletop. And so in the real world, we have a lot of examples of this rotational motion here with propellers. We got pulleys, we got gear ratios, that yo-yo I was talking about. We have car tires. We got different belts for your engine and pulleys, and we also have an example here, which is one of many, which you may not think of a collision between a soccer ball and a human face. And so you can see the distortions during that collision that might not be as visible if you weren't looking at it in slow motion. And so this stuff happens all the time, and we want to kind of have some tools to be able to analyze it. So first off, moment of inertia, we're basically going to first look at the idea of center of mass, or center of gravity, or centroid. And so we understand that not everything is made of point particles with no volume. Not everything is equally distributed in terms of its mass too. I mean, just think about the human body with the different organs in different places and the different densities. You can take an average of all of that and you can get an idea of where your center of mass is. And you can experimentally kind of determine it as well. But the idea is that we have different masses that can come together to make a center of mass. And so the basic idea is you kind of have this weighted average. Like if you wanted to take the sum of 5 numbers, you would add up the 5 numbers and then divide by the amount, 5, right? And so it's kind of like a weighted average. So you're adding up the summation, all of the masses multiplied by their position, and then you're dividing by the total mass. And so I'd like to think about it as a weighted average here. And just recall what this summation notation is all about. So that's the basic idea of center of mass, is we're combining different masses together potentially to get us to a total mass where we have some center of mass that's basically representing all of the mass. And so we apply this idea as well to the moment of inertia, or rotational or angular inertia. It still has to do with mass. Mass is very similar to inertia. Remember, inertia is basically an object's tendency to resist changes in motion. Well, this idea of rotational inertia is an object's tendency to resist changes in rotational motion. And so it's kind of like rotational mass in a way. And so we have this moment of inertia. We use the symbol I a lot of times to represent that. And we can determine moment of inertia about a different axis, so like x, y, and z axis. And so for a point particle, we would just take the mass and then multiply by the distance away from the axis that it's rotating about and square that. And then we got to add them all together. And so I like to draw some similarities here between this and the idea of center of mass. And you have different objects that have different amounts of resistance when they're rotated. And so notice for each of these you have some sort of an object, and then not just the object, but it tells you where it's rotating about. And then there's some sort of a formula here, which is basically representing the result from an integral over the density of that object. And we can get a decent idea of how much resistance to rotational motion that sort of object and axis would experience. And so the other cool thing that we can do with this idea is we have these two theorems that help us, the parallel axis theorem and the perpendicular axis theorem. And if you know for example, the moment of inertia about this, centroid here. We can add some sort of moment of inertia due to this distance that you're, basically rotating around a parallel axis, an axis that's parallel to this, and it's a certain distance away. We can get the new moment of inertia about that axis over here. And same idea with the perpendicular axis theorem. So if you know the moment of inertia about, the x and the y-axis, for example, the z-axis is perpendicular to that, and so we can kind of solve for the moment of inertia about that axis with the perpendicular axis theorem. And so it's all of this here is about finding the resistance to rotational motion about a particular axis for a particular, object. All right. Now, the other thing that this brings up is the idea of kinetic energy. Now that we have things rotating, we have to remember that we're not always talking about 1/2 mv squared anymore. We also have rotational kinetic energy, which is 1/2 times this I, which is that angular mass. Notice how that kind of replaces the mass, times the angular velocity squared instead of the regular linear velocity squared. Now the total kinetic energy a lot of times can be viewed as the translational plus the rotational plus the vibrational kinetic energy. And so keep that in mind as we start to talk about more rotations and angular motion. So the idea of an extended system is this idea that objects can rotate, vibrate, they can change shape as they move. And so that's kind of relating back to that idea of the center of mass and this new idea of moment of inertia as well. But the idea is that not every part of the system necessarily moves the same distance as the center of mass moves. There's different parts of your system that are moving. The center of mass may be moving a certain distance, but a certain part of that object may not move the same way. And so we're getting into this idea of internal energy changes that can be accounted for, and the particles in question, they could be spread out, or they could literally be the parts that you subdivide of the system. The other idea that we have to understand can be kind of visualized by this wrench being thrown. We understand that basically if you model this system as a point particle, it's exactly the same as the pathway of the center of mass of an extended object. And so you have this idea of an extended system or an extended object, but it doesn't really change the trajectory here. But you can see how different parts are rotating as it's thrown, which is kind of cool. The other idea here is for a solid extended object. It basically provides us with the precise form that the law of inertia has to take. And so in the absence of external forces, the center of mass will just move on a straight line with a constant velocity. Whereas the object itself may be moving in any way that does not affect the center of mass trajectory. And so we see that again with that wrench. And so it's not affecting the motion of that wrench, is not affecting the center of mass trajectory. Okay, so that's the basic idea of an extended system. We're extending the idea of a system to account for parts that we might not usually care about. All right. So we'll apply this to a couple problems here. The first problem is a string wrapped around a uniform disk, and we have these masses that are attached as well, a certain distance away. We have a mass of this disk here as well with the radius. And what we're going to do is with your hand, you're going to pull the string straight up with some sort of a constant force. And while your hand is moving up a distance L, the apparatus moves downward a distance h, and it's going to have some angular speed associated with that. And we are given some formulas here for the disk and the point mass. So if you remember back, we can kind of add those up. So the masses times the distance away squared, and we can add those up to get our 4 mr squared. and then we have the disk as well. So we have a certain amount of total resistance to angular motion here. But we got two parts to this problem. One is to determine the change in translational kinetic energy in terms of the relevant variables. And then the other one is to determine the angular speed of the apparatus. And so what we'll do is we'll use the energy principle here, and we will assume that there's no interactions with the surroundings like aerodynamic drag and so on. We'll assume that there's no significant changes in thermal energy. We'll assume that the low mass rods have a negligible moment of inertia. These rods here that are connecting the masses. Otherwise, we would have to account for the mass of those rods as well. And so what we'll do is we'll start off with part one, and we'll go with a point particle system. And we'll have the system being the apparatus and the string, and we'll have the surroundings being the earth and the force by your hand. And the general strategy here is we are going to set the change in translational kinetic energy equal to the work done by the net force. So this is pretty much the work kinetic energy theorem. And so the left side can be expressed in terms of the center of mass, and then the right side is going to be having to do with the work done by the net force. And so for part two, it'll be very similar. We'll look at the differences here. We're going to use the idea of an extended particle system. And for here, notice how we have to account for the rotational kinetic energy. And we also are looking at the work done by all forces, not the work done by the net force. And so we'll see how this kind of plays out here. So for part one, we will look at the energy principle for a point particle system. And so we know that the change in translational kinetic energy is equal to the work done by the net force. And so we have this net force times the displacement of the center of mass is going to give you that net work done. And so we know that we have a final amount of kinetic energy, but the initial kinetic energy is 0. It's not moving initially. And the net force, we're going to have the force of the hand upward, and then the force of gravity downward. So the hand minus the force of gravity times, we're going to have delta y cm here for the displacement. But remember that that's going to be negative h. The displacement of this is going to be negative h because we're going down. It says that the apparatus moves downward a distance h, and so that's an important result there with that negative sign. And so we'll plug in the 1/2 mv squared, and we'll plug in the mass, total mass times gravity for the force of gravity. And then that's basically it, right? I mean, we don't really have any numbers to plug in. So now we have an expression that kind of represents the translational kinetic energy. Now for part two, let's basically take this idea and of an extended system and use it. And so we have this change in translational kinetic energy, but we also have that rotational as well. And then we're going to look at the work done by the hand plus the work done by gravity. Instead of the net, we're going to look at the total. And so we have from before, from up here, we have the change in translational kinetic energy expression, and we're trying to find the angular velocity. And so the work done by the hand is going to be the force by the hand times L, right, upward. And the work done by gravity is going to be negative here, and mass total times g times the distance of that, which is negative h. So we have an expression for the work done by the hand and the work done by gravity. We also have this idea that the total moment of inertia, as I was saying a little earlier, would be the 1/2 mr squared from the disk, plus you have these 4 point masses as well. So 4 times m times the distance away from that rotating axis. And so the distances are always measured from the axis of rotation. And so what we'll do is we'll kind of substitute in here, and we will get this expression for the change in kinetic energy translational. We'll plug that in. We have this idea of the change in kinetic energy rotational, which is just going to be the 1/2 I omega final squared, and then equals, we got the two works added together. And so when we substitute in the total moment of inertia here, we can do that, and then we can do some algebra and kind of clean it up a little bit, and we're solving for this this final angular velocity, and we get a nice expression here. And so that kind of illustrates how you can kind of ignore the rotation at first by using kind of a point particle system that does not include rotation, and then you can look at it as an extended system. You can include the rotation, and you can also do some things as well. And so it just is a nice tool that we can use here with this idea of an extended system. All right, and so we'll go on to the next problem here. So for problem 2, it's a compressible piece of jello, and we're holding it initially at rest here, and it's going to be dropped, and it will move basically a distance d here before, just before it hits the tabletop, and it'll have a certain amount of velocity there. And that's usually where a lot of problems stop, is they want to find the velocity at the bottom right before it hits. But in this problem, we're actually going to consider that, hey, the actual final velocity is at rest. I mean, we all know, you throw something on the ground, eventually it's going to hit the ground, and after that collision, it's going to come to rest. And so, but it'll come to rest, and there'll be some compression that happens as well during that collision. And so we're going to kind of account for that as well. And so for part 1, we're going to look at the translational kinetic energy. And for part 2, we'll look at the change in internal energy, and we'll see what's going on with this. And so we're going to use the energy principle. We're going to assume that the jello's interactions with other things in the surroundings, for example, aerodynamic drag, is negligible. We'll assume that there's no significant changes in thermal energy. So we'll kind of assume that it doesn't like heat up significantly during the collision or something like that. And so we can kind of better account for the energy. And well, in real life, things are more messy than that, but right, we have to make some assumptions and approximations here. And so what we'll do is, for part 1, we'll look at point particle, and for part 2, we'll look at the extended system. And so it's kind of similar to problem 1 here. And our system is the jello, and the surroundings is basically the earth once you release it. And so the general strategy here for part 1 is we're initially at rest, and we know that the final point that we're going to be dealing with is right before it hits the table. And so that's what part 1 is focusing on, just before it hits the tabletop. And so we are going to set the change in translational kinetic energy equal to the work done by the net force, which is really just gravity. And so it's very similar to the last problem. And so it's basically the work kinetic energy theorem. And so we'll have this idea of the change in translational kinetic energy equal to F net times this distance that it was moving. And notice how there's no movement happening really in any other dimension other than the y. And so you could say, 0, comma, negative mg, comma, 0. So the only force is negative mg in the y direction. And then the only displacement is negative d. So we're not including that additional distance yet. And so when we do that, we have... notice how we kind of have those two negative signs, and so we get a positive at the end. So the change in kinetic energy is positive, which we kind of knew because we started at rest. We didn't have any kinetic energy. Then we're dropping it. We're going to be gaining some kinetic energy as we're falling, and we're going to be losing some gravitational potential energy. And so our change in kinetic energy is going to be a positive mgd. And so that is basically all part 1 is about. But now we're going to kind of look at this collision, and we'll look at the internal energy change. And so we'll use this idea of an extended system. And so for part 2, we'll have the change in kinetic energy plus the change in internal energy. equal to the sum of the work done by each force. All right, and so the left-hand side is going to be 0 because it's initially it's at rest initially and finally. And so if we look at the entire thing here, initially it's at rest and finally it's at rest. And so overall during that process, there was no change in kinetic energy, which is interesting to think about. But clearly that is kind of boring unless you look at what's going on with the internal energy. And so what we can do is set the change in kinetic energy translational, which is basically 0 because our initial point here is at rest and our final point is also at rest. And we're going to have that internal energy as well. And then we're going to look at basically the sum of the work done by each force, but we're really only looking at gravity here. And so we'll have the work done by gravity, and so we got the force of gravity times the distance. So it's very similar to what it was before in this case, but we do have a different distance. And so the distance here is not d, it's a little bit farther than d. So it's actually going to be expressed by h, which is the total here, minus b. And so it goes a distance of h minus b. And so our change in internal energy here is mg and then h minus b to represent that new compressed the displacement. So hopefully these two problems illustrate what's going on with the idea of an extended system versus a point particle system. Also, we saw in the first problem how we're dealing with moment of inertia, and we're starting to look at rotation, and we will look at that a little bit more as well. We have an example here of a collision, or we're starting to at least think about collisions a little bit more as well, and so we will see some more examples of collisions moving forward too. And so we will see you in the next one.